All right, for today, I would suggest we try to cover a bit about the lecture material. I would really love to finish the initial model, especially about deadlock freedom today. And then, if time permitted, we'll definitely talk about your lab number 2 and also your programming test 1. I think these are also important. I will try to make sure I cover all of them today. But let's continue with the lecture a bit. And what we discussed last time was actually very fundamental because the approach that we have been using is going to be something we apply to the subsequent refinement as well. So let me just, again, at the conceptual level, let's recap what we really did last time. Right? Always remember the flow. You're given some initial model, right? So this will be the model, which has, of course, constants, axioms. So these will be the static part. Also, you got variables, you got invariants. And don't forget, you're also given a set of inference rule. Okay, so this is the new bits that we kind of covered recently. Inference rules. Right? So you got different sets of the inference rule. We're going to see a second set today in order to prove about deadlock freedom. And from the model, what can we do? We basically want to argue about its correctness with respect to certain criteria. And the criteria that we talk about so far is about invariance, for the machine. So we're going to generate proof obligations. Or POs. And the way we specify proof obligation is by using sequence. And you can find so many examples from last time, right? So hypothesis and the sequence and this, right? A set of them. So far, we talk about two kinds of proof obligations. One is for invariance establishment. It's like a base cases for mathematical induction. And also invariance preservation. These are like inductive cases for mathematical induction. What's really missing from the initial model is the deadlock freedom, which we'll talk about just after the recap. And I want to say one more thing. You may not be lucky in general, just be able to prove whatever sequence you generate, which we illustrated to you. You might find that some sequence just is provable, just is unprovable. In which case, you have to go back to your model over here and change some of them. What we did last time was after we changed the events, I forgot to mention events. Let me put it down. I went back to the events, both of them, and look at their guards and try to add something to strengthen the guard. And that somehow regenerates the sequence, and we can prove them. And today, we're going to see another example. We're going to generate the proof obligation sequence for deadlock freedom constraint. And we found that it's actually not provable. In which case, we have to go back to the model, and this time, we don't really touch any of the events. We touch something else. Okay? So let me write this down. You really want to get this picture clear. And for this sequence over here, you want to know, in general, not necessarily provable. Provable. Okay? In case it's not provable, go back to the model. If it is not provable, any one of them, that means fix the model. And you do some fix over here. After that, you have to regenerate all the sequence, right? That'll be the subsequent step over here. And after regenerates all the regenerating all the sequence, try again to prove. This will be like an iterative process until all the proof obligations are discharged. Right? That's really the picture I want to keep in mind. And what's going to be new later in the course is we're going to keep adding the kind of proof obligation you can actually prove about your system. Today, we're going to talk about deadlock freedom. Later on, we have to do some proof obligations specific to refinements. We haven't got any refinement just yet. But later on, this set over here will be grown. But the process over here will be just the same. Right? Keep that picture clear in your mind. Guys, any questions so far, please? We okay? All right. Okay, let's now move on. And this is where we were. One more thing. So if you look at the page, the last page from last class on Tuesday. So this is basically our initial sketch about deadlock freedom. What does it really mean when your system might run into a deadlock situation where all the events are disabled? So the opposite way to look at that would be, what would be the condition where it's deadlock free? Right, that's something we want to speak about. Okay, let me go back to the slide to show you a little bit, and then we can formulate things. Okay, deadlock freedom. And that's what we spoke about so far. And it might, there's a possibility of deadlock for your system, in which case all the guards are false. So we want the opposite. We want at least one guard that's actually true, right? And then when the deadlock happens, none of the event is enabled. That's pretty straightforward. And then we want to express this non-blocking, non-deadlock property as a new requirement, right? That's where we were. Let's now move on. Deadlock freedom. Okay, and let me just go directly to the page. In order to formulate deadlock freedom, we need some new components for formulating it, right? So this will be the sequence that we have to formulate. It's not too bad, but let me just walk you through very quickly. Again, this is our model, and notice that I already fixed the guards for the two events, right? We're going to carry on from our work from last time. So we still got our list of constants. We got our list of axioms. That's exactly over here. And also we got v and v prime in the pre-state and post-state for the variables. We got invariance, and here we got event guards over here. And notice that the guard over here is for a specific event. And now, if you want to express about deadlock freedom, you have to consider the guard for every event. All right. Let's now take a look at the new rule. The new rule is called DLF, standing for deadlock freedom. It's obvious. Okay. And then we're going to look at what can be the hypothesis for which we want to show this is true. Hypothesis would be we're going to assume the axioms and also assume the invariance in the pre-states, right? Let me just remind you quickly. All the axioms and also the invariance being held at the pre-states. And now I want you to look at the consequence over here. Okay, the goal. Here, we are saying it's going to be the guard of event number 1, and then the guard of event number 2, all the way to the guard of event m, assuming that we got n events in general. But if we only got 2 events over here, the n will just be equal to 2 in our case. N will just be equal to 2. And we try to disjoin the guard together. So let's think intuitively. What do we want to really prove over here? We want to say the disjunction of the guards of all events true, held true. Now, guys, question. Do they hold true in the pre-state or the post-states? According to the formulation. Pre-state, right? Because V here is V, not V prime, first of all. Very important. I'm going to give you a little bit more intuition. That could be a confusion at some point. So think about the V here is the pre-states. So this is a very important observation. When you try to formulate about the deadlock freedom, you do not care about the post-states, because deadlock freedom is really about whether the event can even be enabled in the first place. After the event has taken place, the effects of the event for the action will take place. In that case, you have to worry about invariant preservation. You see what I mean? Okay? A little bit diagram might help. Okay? So if you don't mind, let me draw here. Okay, over here. Think about this is some arbitrary states of your system. Okay, some arbitrary states. And then this will be the post states. And of course, conceptually, you may take some events over here, events, just arbitrary event. Okay, event number 1, event number 2, and etc. to the different post states, right? Okay, what's really about deadlock freedom? Deadlock freedom is really about the pre-states. Deadlock free if at least one event is enabled. Right? That's all Deadlock Formulating is concerned about at the pre-states. At least the transition can take place. If, let's say, event 1 over here is enabled, in that case, the transition will take place, in which case the action of event number 1, the before-after predicate, will be applied to the system variable. In that case, this post states over here should satisfy the invariance, right? That's about invariant preservation. Okay, so over here, after the event's action takes effect, invariant should be preserved. So there's one little very quick exercise you can do after today. I want you to really go back to look at the proof obligation rule for invariant preservation. You will see that we are really concerned about the post states where the invariant actually holds. On the other hand, for the Deadlock freedom, we're only concerned about the pre-states, which we talk about now. All right? Guys, are we okay so far? Okay, good. And given this, all right, how do we formulate it? And then I will make some table to help you even further. But before that, let's try that. Okay, let's try. Let's start with the axiom, which is obviously just over here. So we got a member of natural number. Also, we got, let's say, the invariance. Let me use maybe different green. All the invariants in the pre-states. We got n should be a natural number, and also n less than or equal to d. That'll be the hypothesis. Okay? And let me just draw horizontally. What will be the goal? Anybody want to try? Anyone? Yes, please speak up. The guards? Yeah, just tell me exactly what I should write. Conceptually, yes, you want to disjoin all the guards together, right? In this case, how many events do we have? 2? Yeah, tell me the guards. This is one guard. This is one guard, right? And how should we put them together? Disjunction. All right? Let's do that. So what I will do is I'm going to put n less than d, or n larger than 0. So this one here is the guard of ML out. This one here is the guard of ML in. That's it. I would say to really formulate the Deadlock freedom constraint is actually easier, more straightforward than the invariant preservation, because if you recall what we did earlier, if you wanted to do for invariant preservation, you have to say m prime, for example, right? And then you got to replace the m prime according to the before-after predicate for that particular event. That's what we did before. But we don't need to do it anymore for Deadlock freedom because it's only concerned about the pre-state. Right? That's something you want to watch out for. All right, guys, any question so far? Good. Let's now make a table, all right, to actually help you understand a little bit more. So far, we talked about 3 kinds of proof obligation. So let me draw the table here. Okay. Let me make a little bit more space here. Okay, so for the so let me say the proof obligation, right? So we talk about invariance establishment, invariance preservation, and also Deadlock freedom, right? So these are the 3 proof obligations we spoke about. And I want you to really think about, in order to really formulate each one of them, what states should be involved in terms of pre-state. One example, that's the easy one. So we got the pre-states, namely just the V, right? And also we got the post-states. The post-states. which is the V prime, right? Okay? I'll start with the easiest one. For invariant preservation, we want to make sure at the pre-states, the invariant hold. At the post-state, invariant maintain. So both of them should be involved. You can check this out also in the actual rule. So I'm going to say, yes, both of them should be involved. All right? Now, guys, what about this one? If I want to formulate invariant establishment, which we spoke about last time, what should be involved? Post-states? Okay, very good. Because in the init events, pre-state doesn't make sense. It's the very first one. All right? Very good. So that means not good. Post-states. And the Deadlock freedom, just the pre-state, right? Do you need to memorize the table? Not really. Just try to use it to help you understand the various kinds of proof obligation. I would say, hopefully we can finish almost everything about initial model. Try to review it before next Wednesday's class. And we're going to start about the first refinement. We got 2 refinements in total to talk about. Okay. Just give you some look ahead. Okay. All right, if no question, let's now move on. Let me see what's the next one. Okay, Deadlock freedom, and that's one we just formulated together, which is very good. Now, can we really formally discharge this sequence? That's the question, right? Basically, you have to start with this sequence over here, and then try to apply a set of inference rule. Have some proof tree, and then see if you can end up with all axiom inference rule. Okay? We'll try together. Don't worry, this one I'm going to do it together with you. In order to do this, we need a second set of inference rule. Let me first of all show you. I already made it online on your lecture site. Let's take a look. Okay. I'll show you where you can find them, and I'll go over with you each one of them. Right? So let's do that properly. I'll say this coming proof is going to be a little bit challenging, so let's do that carefully. There we go. All right, so if you go under this part over here, you will see example inference rule number 2. Right, so these are the ones we may have to use for today's proof about Deadlock freedom. But let's go over them. All right. Let's start with the simple one. Let's go with the green ones, which are terminating cases for inference rule. The first one is called hypothesis rule. This one is, again, don't forget the big picture, the structure. In order to prove the consequence, it would be sufficient to prove the antecedents. But it's not there, so nothing to prove. That means it's true automatically. What is this saying over here? Can anybody try to gain some intuition? Why can this sequence here proved automatically? Ryan?
Because the answer you're trying to prove is already the thing that you assume to be true.
Exactly. That's spot on. Exactly. The answer you're trying to prove over here is already assumed to be true. Absolutely. Spot on. Okay? So this one is good. Okay? You can see they match. Okay? That hypothesis rule. And here, again, you want to really understand the naming convention over here. When I say false L, the L here is similar to what I said earlier before the reading week, right? Just remind you, L means it appears to the left of the turnstile. The left of the turnstile. So here you can see the false over here. Right? So if you already got false as the antecedent, nothing to prove because false implies anything. That's easy. Symmetrically, you can see true and R. That means the true appears to the right of the turnstile. And now, if you already got something to prove to be true, true is always provable. Doesn't matter what you have as part of the hypothesis. Right? And finally, EQ, equality. If you got something like something is equal to itself as the goal to prove, it's also provable because something equal to itself is always provable. Right? Are we okay with 1, 2, 3, 4 over here? These are easy. Oh, I shouldn't say easy, I say more straightforward to think about. The next 2 are potentially very confusing, but we're going to do example, don't worry. But let me explain at least how you can understand that. here, let's understand the name. Go ahead.
P implies E equals E. Is that saying that P implies E is the same as E, or that P implies that E is the same as E?
This means P implies E equals E.
Okay, good.
Good. Yeah.
Yeah, that's okay. Yeah.
Yeah. I'm glad you asked, but for what it's worth, why don't we try to put it here? P implies E equals E. But equality takes precedence anyway than implication, so it's worth emphasizing. Very good. All right, so let's understand these two red ones, and then we can go ahead to do the proof. Okay. So EQLR and EQRL, they have different rules, even though, well, by first glancing them, they look the same, but they're different. All right, let's take a look. First of all, LR over here tells you, okay, LR tells you the application. I'll explain what application is. Application from left to right. And RL over here tells you the application should be from right to left. Let's see how. Application from right to left. All right? Let's understand that. Oh, why don't you guys take a quick look before I tell you? Take a quick look. The only hints I want you to keep in mind to start with, we are saying that to prove this, it would be sufficient to prove this.
Okay.
Okay.
Yeah, that makes sense.
I'm glad it makes sense to you, but let's see if that makes sense for everybody else too. All right, good. Okay, let's now have some explanation. We're saying the following. If you can assume that E is equal to F, so E here is the left-hand side, F is the right-hand side. And at the moment, we are actually having some goal to actually prove, and the goal depends on the left-hand side expression here. Basically, the hypothesis and also the goal that we want to prove. Oh, sorry, let me say it again. The hypothesis we assume and the goal that we want to prove, both of them rely on the expression E, which is the left-hand side. Okay? Left, left, and left. And it might be worth to use a slightly different color. If this is what we want to prove, it would be sufficient to prove a different goal with a different assumption, as long as we replace every free occurrence of E by F. Every free occurrence of E by F. We are basically proving the same thing. That's what it is saying. Okay? So you can think about this part over here is about H of E replaced for free occurrences of E by F. And similarly for this one here. And now you can see the way we do replace, that's really the application I'm talking about, the replacement. We'll basically go from the left to the right. And also here, from left to right. From left to right. All right? That's the EQLR. But of course, we're going to see how to use it. Another one, which is basically the same. E equals F is still the same as before. But now we want to prove something, assuming something, but that something all depend on the right-hand side. What can we prove? That'll be sufficient. We can, well, prove the same goal and try to assume the same thing, except that we replace the right-hand side by the left-hand side. Right? Okay. So here, again, think about what's happening here. This is the left. This is the right, right? And then we can now try to prove something in terms of the left instead. And the left. And the right, and the right. So we basically go from the right to the left. So that's why it's called it's called RL. All right, guys, any question about this? Yes?
So there's no difference between the E for F
You mean here?
Yeah, if we change the order of
Okay, so this is saying if this is happen to be, okay, let's say if this happened to be what you want to prove. So here, this is the left-hand side. This is the right-hand side. Of course, if you're given something different, then left-hand side and right-hand side will be different, right? We're just saying, let's say this is what you're given. In that case, let's say this is E, this is F, right? If you do E equals F to F equals E, in that case, well, thinking this way, if you say this rather than E equals F, right? If you say F equals E, in this case, F will be the left-hand side, E will be the right-hand side, and then you do the replacement accordingly. Let's do this. Okay, let's say the only thing you want to change, F here, E here, okay? And then if you look at this one here is saying that the goal and the assumption all depend on the left-hand side. Agree? That's F. And you basically replace the left-hand side by the right-hand side. In that case, this wouldn't be called RL anymore. It should be LR. It's really the same thing. So don't really think too much. What you really want to capture about these two rules is about given some equality, right? Put in whatever order you like. Let's say the final order you want to fix. And then this will be the left, this will be the right. And try to see what the hypothesis and the goal actually depend on. Do they depend on the left-hand side? Sorry, do they depend on the left-hand side or right-hand side? And then do the replacement accordingly. And then you will know which rule you're really using. That's the bottom line. I hope that can answer your question. Yeah. All right, of course, when you actually do the proof, you have to use the right rule. Sometimes you might think, oh, I'm really using this one. No, maybe you're using this, right? Or vice versa. But we'll see. Example. Guys, final chance. If you want me to dive deeper into any of the rule, please say it now. And then we have to do some proof to exercise. Okay? And I would suggest let's do this proof, and then we'll realize this proof actually cannot be completed. I can even tell you first. And then we'll take a short break, and then we'll revisit. Okay? Let's now try that. Okay, these are all the inference rules. You can also see some explanation on the slides, which should be consistent with what I just said to you. And this is a little bit more formal writing. You can take a look too on the slides. Okay? And this is what we want to prove, right? Deadlock freedom. This guy over here. I want you guys to take a look at this. Just take a look at that. See what can be assumed and what should be proved. Do you think that should be provable or not? Actually, I already told you it's not provable, right? But think about how you may somehow split the structure to make it a little bit easier so we can apply the different inference rule that we had. Again, the one I'm going to show to you is just one possible way to prove it. We'll try to prove it. But if you find another way you want to discuss, let me know. Again, proving is not just a unique solution always. All right, let's now take a look how we can prove it. And as usual, I already told you, I'm already telling you these are the ones you may want to consider using. These are the ones. All right? But I would like to give a little bit idea about how we can make some mental planning before we even try. Question?
If D is 0, and N is 0, this can't be proved, right? That's the case where it can't be proved?
You want to tell me what the inference rules are, right? Well, we'll get there. Don't worry. We'll get there. Yeah. Because you want to, well, no, we're not trying to prove something that's unprovable. I'm just saying, given this, can you see any insight about splitting that into a smaller sequence? At least we can see the smallest unit that's unprovable. We don't just want to say, oh, this big thing is unprovable. That wouldn't help too much about fixing your model. Okay? Okay, so guys, again, since I know the answer, so let me do a little bit faster for you. So I will give you some insight. You got to think about it. All right. The main thing you want to consider is this. You can see the goal over here. Again, this is the guard of one event. This is the guard of the other events. We want to prove that at any particular state, either this is true, that means the event is enabled, or this is true, that the other event is enabled, at least one. Okay, that's what we want to prove. And it involves N and D. The obvious one to really consider between N and D will be here, right? That's what we have. Okay. Of course, natural number here, just larger than or equal to 0, larger than or equal to 0. Usually, you may not need any typing constraint. Usually. Okay. And if you guys remember, right, just temporarily, this guy here, we can rewrite it, right? N less than D or equals D. First of all, right? And take a look. This guy here matches this. If somehow we can isolate these two so that we got this as the hypothesis and this as the goal, we're done with that particular branch. Okay? And then this guy over here is about equality. That means we might be able to do some replacement. For example, here we say N is equal to D. Now, you got two possibilities. Either you can say replace every occurrence of N by D. In which case, replace this by D. Replace this by D. In that case, this D less than D is false. False or anything will just be that thing. In that case, you're really trying to prove D larger than 0. Right? That's one possibility. The second possibility, you may want to replace every occurrence of D by N. In that case, you basically want to replace this by N and this by N as well. This, again, is false. And you basically want to prove N larger than 0, either way. Okay? I'm just telling you, in general, this is what you should really try. Okay? Let's give it a try. So I would suggest we, first of all, this guy here into this. And then we can see how we can isolate these two cases that I just talked about, right? That's what we should do. All right? Question?
Okay, so first, the case where N less than D, that's trivial. If N,
Yeah, I know it's trivial, but let's do it together, and then we'll see how trivial it might be. All right. Okay, let's now try. First of all, let's do some basic arithmetic. So I'm going to say arithmetic, right? ARI. Okay. Usually, if you do some very basic rewriting like this, you can say arithmetic. Okay. And then we're going to say this. So the natural number and natural number the same, and also N less than D or N equals D. The goal doesn't change. You only do one change at a time by applying a single inference rule. N less than D or N larger than 0. Okay, so here is a very important thing for you to remember according to the rule. I want you to take a look at this one here and, for example, this one here. These two. That's why understanding the naming convention for the inference rule is so important. This one here, which we learned first. If the disjunction appears to the right of the turnstile, which is over here, that means we want to prove something that's disjunctive. I want to prove either this or this. That means I can drop either one of them. Agree? I can either prove P, that'll be enough. Or I can prove just Q, and that'll be enough. Right? So that's the case where you got disjunction in the proof. In that case, you can drop either one of them. Okay, just remember that. On the other hand, here I got ORL. If the disjunction appears to the left of the turnstile, you cannot drop any one of them. Instead, you have to discuss in two cases. Since I can assume the disjunction, so I need to think about what if I assume just P? What if I just assume Q? Both of them should actually work because either assumption may occur. I don't know which one. So I want to make sure either one of them, whichever occur, should work. All right, question? Which one? You mean here? Yes, in this way, yes. You can see here if the assumption is a disjunction. In that case, you will split a single sequence into two separate sequences, right? In that case, you gotta discharge this and this separately. But in some way, it's not bad because in that way, you only got a single P to assume. You also got a single Q to assume. In some way, these individually are simpler than this. Okay? Question? Separately, yes, independently, I should say, independently. Let's do that right away. All right, before that, as I said, these two may not be so necessary, so let's drop them. And what should be the rule I use? Monotonicity, all right? I'm still thinking about how to test you guys about pronunciation, maybe in the exam. I'll think about a good way. Okay. All right, so that one should be monotonicity here. And then let me drop these two, all right? So what I will get is I'm going to get n less than d or n equals d. And then turn style, n less than d or n larger than 0. So far, so good. All right? Yeah, to really make myself some space, I'm going to do something. But you don't need to do it, don't worry. Only for me. All right? Now, we want to really worry about these two. We want to worry about these two hypotheses independently. Because thinking about a big compound usually is harder. All right? So we should apply this rule. All right? Let's review this rule very quickly. If I got P or Q as the hypothesis, I can move P into the hypothesis of a single sequence where the goals remain the same. There's another separate sequence where I got the right-hand side for the disjunction of the hypothesis, and the goal remain the same. All right, let's try that. So what I'm gonna apply will be called ORL. That one there is going to produce two sequences. All right, let's do one by one. So you can think about this guy here. Sorry, this guy here is like the P. This guy here is like the Q. All right? So I'm going to put number one, n less than d. The other one will be n equals d. And then the goal remain the same. N less than d or n larger than 0. Okay, this is one, and then turnstile. N less than d or n larger than 0. Say that again. ORL. That's what we're using. Yeah, for the top one, yeah, don't go there just yet. You know, we want to get everybody to look at that. Okay. So guys, would you think this might be provable? Getting very quick, right? Getting very very close, right? Because you can see somehow this appears over here. But I want to give you some warning. Here we are lucky because the one we want to prove is a disjunction. So that means if you want to prove something that can be this or this. So as long as I can prove this, I can do it. Later on, we might run into a situation where we want to prove both. In that case, you cannot drop one of them. Right? Just remember, the symbol here is really important. That also captures semantics. All right, so here, because we want to isolate these two, so let's drop this. According to ORR1. Oh, question for you. That's also very important. Let me show you what I should write over here. So n less than d and also n less than d, right? This could be a multiple choice, maybe in your written test number 2, right? Let's say I give you these two sequence. What should be the inference rule that relates between them? Should it be ORR1 or ORR2? R1 or R2? R1, okay. Why? Because think about this is R1, this is R2. Which one do we drop? Oh, sorry, which one do we keep? R1. All right, so OR1, yes. All right, so OR. Oh, sorry, let me just make a little bit more space. Yeah, we'll definitely finish this proof, and I think it's really important. Okay. OR, R1. All right. And now, apparently, this guy here, as your class may observe way earlier, this one here is really corresponding to this. Don't you agree? Hypothesis, because P appears in P, right? They appear both places. So, hypothesis. And done for this branch. So let's reflect very quickly. The reason that we could really discharge this branch easily should be with thanks to this rule. Because originally, we got disjunction here, which means we cannot really consider each one of them in isolation. But after we apply this rule over here, we were able to actually consider them separately, and then we can discharge this one first. Right? All right, so now we want to handle this guy over here. All right? And let me make it a little bit smaller. I would say, since we already learned about the equality rule just a few minutes ago, right? Anytime, I would say, if you actually got some equality over here between two variables, it would be very worth trying to see whether you can do some replacement. Okay? Not necessarily going to be a very good strategy every time, but I would say most of the cases, at least for this course. Okay? Let's try. And again, since I know the answer, so let me say, why don't we try EQLR for now. And for those of you who might be curious, which is completely legitimate, if you really think, what if I try EQRL? Try it as well. You'll run basically into the same conclusion. Okay? Let's do this one first. So what I want to do is to have EQLR. EQLR. All right? Now, here comes the confusing part, exactly how to do replacement. All right? Let's revisit the rule. Think about this. Well, first of all, this is the equality, right? And then you can think about this guy here. Oh, let me just try to do some highlighting. This equality here is really corresponding to E equals F, first of all, right? So think about this guy here is the E. This guy here is the F. And at the moment, the thing we want to prove can be defined in terms of the E, apparently, because N appears over there. So if we want to apply the EQLR, we're basically going to replace every occurrence of E, which is N, by F, which is D. That's what we're going to do. All right? Let's try. In that case, I'm going to draw just another one over here. And one thing to note, according to the rule, after the replacement, E equals F should still be there. You shouldn't drop them, right? Unless you apply monotonicity again. All right? So we still got N equals D over here. And then, okay, so let's now try. We're going to replace, let's do some rehearsal. N here should be replaced by D. N here should be replaced by D, right? Let's write it down. So D less than D, or D larger than 0. Yep. We'll take a break very soon. Just bear with me. Okay. And obviously, so here you have two choices. Okay. Either you can say this expression over here can be simplified into false or D larger than 0. And then we know false or P will just be equal to P. You can apply the basic arithmetic and simplify to get rid of this part. That's one way. Or we can use the OR R2 to keep this one. Okay? So it will be OR R2. Let me use that one. Finally, we can say OR R2. And what we have is over here. Okay? N equals D, and then I'm going to drop this one here, basically. So D larger than 0. Okay, that's what we have. Okay, just let me do one more thing, and I'll answer your question. And in this case, n equals d is not really helping d larger than 0. So I would suggest we further simplify what's really unprovable. Okay? So for now, I'm being a little bit lazy here. Don't be like me in the test. So I'm going to say, after this, I'm going to apply monotonicity. All right? That will allow me to drop the only hypothesis, which is not very useful. That's what we have. And this guy over here is unprovable. This is to say, we are not able to prove that d is always larger than 0. Okay? What's d, by the way? Do you remember what d is? The number of cards you can actually have. The maximum number of cards you can have in the compound of island and also the bridge. All right? Just keep that in mind. All right? So guys, before I let you take a break, I think we should definitely take a break. I don't want to bore you too much about the proof. But I think the conclusion, and then we're going to pick up from here after the break. This guy over here is unprovable. And according to the workflow I try to visualize to you, if something that's unprovable, what should we do? Go back to the model, change something, and then come back. All right? That's what we'll do after the break. Why don't we take attendance and then take a break? And then we'll continue with this. It wouldn't help. Okay, very quick. Apparently your classmate doesn't want a break. Let's answer that quickly. So here, yes, indeed, one of the possibilities, let's say I keep let's say I keep this one here, right? It's all the way here. D is a natural number. Would it help? Well, D is a natural number. Remember, that only means D is larger than or equal to 0. I'm glad you mentioned that, but it wouldn't help. Good thought, but it wouldn't help. Okay. All right, let's now take attendance. All right. 2342, and then start the class. All right, check in, please. Yeah, we're now taking attendance. If you're not doing it, please do it now. You got it, don't worry, no rush. Everybody's good? Attendance? Okay. All right, guys, 2 minutes break, and then we'll come back. Yes, question. Yeah.
So when we're doing proving, is this our last step when we reach the hypothesis? That's it?
That's exactly right, because the hypothesis is actually an inference. You don't need to do anything else for this branch.
Yeah, so that's it. So you basically, your goal is to reach hypothesis.
Yeah, well,
When proving.
not necessarily a hypothesis always. You want to reach a rule that's green, that's terminating.
Okay, yes. All right, thank you.
Okay, good.
I can go to the last page.
Last page? Yeah, over here.
Okay. Here you say we are using the LR, right?
Mm-hmm.
So as the result, we should keep the E.
As a result, we should, no, we don't keep the E. We want to replace the E by F. That's what we do.
Excuse me, we get a no response on the answer.
But it's like...
Here you can see, you used to have E, right? And then you want to replace the E by F. That's what you do.
No, I think as long as you click it in, it's fine.
this is we assume to be true, and then the second one will be true, right?
You may want to review the basic meaning about inference rule.
Oh, I see.
Yeah. Why don't you review them a little bit and then we'll talk later. Okay, good. Didn't work for you?
No, mine's just, I don't know, lag, so can I just sign in?
Of course you can. Do you want to bring the pen so every one of you can use?
I'm not sure if mine didn't record or it recorded, but it says no answer. For
Why don't you sign anyway? So
Okay.
yeah, we can look at that. Yeah, just wait for the pen. Didn't work for you?
Close before I could put it.
Well, do it quickly, right? Right. Question. Go ahead. Of course.
Why would we not continue with this?
Yeah.
Is
So
it because this would already be false? prove
Yeah,
that
exactly.
it
Because if this is already false, and false wouldn't really make any contribution to disjunction, so we just drop it.
Okay, so we have to prove that both of them are
Exactly.
false.
On the other hand, let's say this expression here is directly true. In that case, that's good news because true or something is just true. You have nothing else to prove.
Okay,
Right?
perfect. Thank you.
Yes. Yeah. Why don't we use your pen and then find your name?
Oh, is it? I need pencil.
Oh, pencil is fine. Pencil is fine.
Where's my name?
Sort it by last name. You can find your last name.
So I just check this.
Mm-hmm. Oh, actually, if you can put your signature as well, please. Thank you. Awesome. Oh, your pen. Yeah. Just before you take it away, if I don't mind. Thursday, March. Is it second or third?
Oh, it's second.
Second. Yeah. I thought it's second. I wish that could be one day more, but you know. There we go. Thank you. All right, we'll start in just one moment. All right, guys, let's get started again. We got about slightly less than 20. Oh, it's 15 minutes. Oh, we got about 30 minutes-ish, slightly less than 30 minutes. Let's see what we can do. I think we should definitely finish the initial model, and then at least I should talk about your programming test one in case you got any confusion. If I cannot go over Lab 2 solution today, what I can do instead, I can release by early Monday some short video to walk you through the solution. I think that might be equally good, right? You can still drop by the office hour on Tuesday and Wednesday to ask me questions if you got any doubts about Lab 2 solution. Okay, so why don't we finish the initial model, and then we will do go over quickly the guide for the programming test one. Okay, and then we'll see. That's at least what we should do. Okay, so that's what we try to prove, and then you'll see on the slides exactly what I did. Oh, the only difference is, you can see here, I put equivalence. I think maybe I should change that. It should be ARI, arithmetic. But if you put that equivalence in the exam, I will know what you mean. But it's better to be consistent with what I said. Otherwise, everything is good, except you can see this guy here is unprovable, right? That's why I put a question mark there. And what we need to understand now is, given something that's unprovable, how can we know how to adjust the model? Of course, the way I'm going to describe it is because I know the solution, again. So I'm going to give you some insight about this is one possibility to consider the fix. And if you're really given something you haven't seen before, let's say in the exam, so I would say you should really say, based on the problem description, based on the hints I give to you, you want to think about how can I fix it so that the sequence can really get discharged. Okay, that will be the bottom line. Okay, let's take a look. All right, let's now, rather than slides, let's be logical. Okay, before that, let's recall. Before the break, this sequence over here is unprovable. We simply cannot guarantee that D is always positive, simply because if you look at the model, here, D is a natural number, right? So D cannot be like a larger than 0, okay? And we want to dive a little bit deeper into it. Okay? So what we want to do is this. When we say this is unprovable, that means the negation of this particular goal that we want to prove may be violated. May be violated. That means its negation may be true. And we want to go, dive a little bit deeper into this. Maybe true. That means not the case. D larger than 0 is allowed by the current model. Let me say that again. This is the sequence that we cannot prove based on the deadlock freedom proof obligation rule. And if this cannot be proved, that means there is a possibility that the current model may violate it. If it violates it, that means its negation is actually true. All right, let's simplify that a little bit. So this implies D less than or equal to 0. Let's call this number 1. And if you remember, we got another axiom over there, which says D is a natural number. Which means D larger than or equal to 0. I think according to one of the piano axioms that we spoke about before, it actually tells you, right? Now, if you got 1 and 2, both possible, what does it really mean? Here and here. If you put these two together, D less than or equal to 0, also larger than or equal to 0. Can it happen at the same time? Are you sure? What if D happened to be 0? In that case, both would be satisfied, wouldn't it? Right? So here, think about, this is 0, right? This guy tells you less than or equal to 0. This guy here tells you larger than or equal to 0, right? So D equals 0 could be something that could be a key for us to revise our model. Okay? Now, can you guys tell me what could be bad about D equals 0? Why?
The maximum card is 0.
The maximum number of cards will be 0. Okay, I agree. Conceptually, if you allow no card to actually go into, not even to allow to the breach, because you cannot go to the compound. So that means neither ML out nor ML in should be allowed to take place. In that case, we got a deadlock. All right, let me be a little bit more specific, more formal.
What kind of bridge are you running? Okay.
Yeah, exactly. Basically, you build a breach controller, you build a breach, a very nice breach, costs you $1 million, and then suddenly you say, no card should be allowed. That's like that, right? So, yeah. Not very good. But that's basically what the value here is telling you. Okay? Let's now go from here. All right? Let's go from here. Let's now be very careful about understanding this scenario over here. Okay? Let's say D is equal to 0. And after the initialization, and remember what value we set the n to be? 0. That makes sense. N being equal to 0 initially shouldn't bother us. Of course, initially no cards should be there, right? N equals 0. And then, now, since we talk about deadlock freedom, consider this guard here, consider this guard over here. In order to be deadlock free, it should be that either this is enabled, in which case this will be true, or this is enabled, in which case this is larger than 0, right? Now, for this particular scenario, let's do some replacement. D will be 0. N will be 0. So what do we have? 0 less than 0 or 0 larger than 0. What should that be? False. Exactly. So this tells you the current model allows the D to be 0, in which case you're going to get a deadlock because none of the events you have for the system can be enabled, right? That's what's wrong. Now, guys, digest. You will need to take some time. I'm just trying to present to you the thinking process. All right, so we know that having D with the possibility of 0 is not good. Let's make it not equal to 0. What can we do? So that means the typing constraint over here, which your classmate also talked about before the break, right? You've thought about whether you should really include this in the sequence. But D is a natural number. It's not sufficient to prove that D is larger than 0. Okay? So what should we do? Well, we just add an extra here to say D should be larger than 0. That's what we got to do. Okay? So the fix goes like this. We want to have another axiom for the same initial model and number 2. Oh, sorry, let me write a little bit correctly. 0 and then 2. D larger than 0. That's what we have, right? So what I just presented is also on the slides. You can also take a look, right? So we're going to fix by adding this new axiom. Now, we basically, again, let's go back to the flow diagram. It is so important to know where you are. If you go back to this flow diagram here, we found that D larger than 0 is unprovable, so we go back to fix the model by adding the axiom to say D is larger than 0. So now what should we do? We should go back, regenerate the proof obligation, and try to prove it again. Right? Okay. So I would suggest 2 things. Number 1, oh, sorry, not here. Over here. Number 1, I'm going to leave. Oh, this is the actual proof. I'll go very quickly with you just to see, okay? I would say I'll leave this page 100% clean. Why don't you print it out and then try to see if you can do the proof. The only difference is you can see there's an extra D larger than 0 because we added 1 axiom. So that's why we can have one more thing to assume. Why don't you try with this, start with this, and then try to see if you can do the proof. Okay, that'll be exercise for you. I'm going to leave it 100% clean. Okay. On the other hand, I want to give you some little bit idea to see how things will go. This is the proof without that fix, which we could have proved this guy here. Right? What's going to happen, you will see, is because we could add D larger than 0 over here. That means we can still keep it over here. After applying monotonicity, we still want to keep D larger than 0. And for the hypothesis one, we don't need to include it. But for this part over here, we want to keep it, D larger than 0. And then ultimately, you will be able, you still want to keep this, and then you keep that. So ultimately, you should be able to apply the hypothesis rule. This one is a very quick kind of reflection about why adding some axiom to your model is going to change the proof tree. Well, the structure itself doesn't really change, but it will allow you to finally discharge this particular sequence, which we couldn't discharge because of the hypothesis rule. Okay? This is something I will do. I just did it with you, but you should really try to really prove it as a brand new example. Okay, so you can practice that. Okay, I'll leave that to you. Okay, so after this second attempt, you should really prove it. But before you look at the solution, I would suggest try to do it by yourself. And now we are able to conclude about the initial model. And then, so next Tuesday when we come back, we can start talking about the first refinements. Okay? And of course, Thursday you got your programming test, which I'll talk about. All right, let's do a quick summary. And I think I do have 1 page for that. So this is the final model we have. Right? Again, I would suggest before Tuesday's class, try to review what we have covered so far about the initial model. When we talk about the first refinements, we're going to be faster. Whenever we talk about anything that we prove something similar before, I'll leave them as an exercise to you. I'll focus more on the refinement. That's going to be more complicated to understand. I'll focus more on that. All right, so you know for the model, this is the static part, right? Just always remember, you got static part, and you got dynamic part. And just remember, these 2 event guards were added for invariant preservation. And this axiom over here were added for Deadlock freedom. All right, and then of course we got initialization as well. And finally, we can claim that our model is correct with respect to 3 criteria: invariant establishment, preservation, and Deadlock freedom. So right, that's the final conclusion we have over here. Okay, all right. All right, any question? Yes. EQR. Yes.
In order instead of change N to we can change the
Yes, you definitely, at this step, yes, you can try to do EQRL. You can do that, but that one there may not lead you to some useful sequence to really give you some insight. So my point is, somehow I'm taking a shortcut because I know what the solution is. So I'm leading you to the final one that will give you the useful insight. If you try EQRL, you're going to have some unprovable sequence as well, but that unprovable sequence may not suggest an appropriate fix to the model. Maybe try to do that, and then we can discuss maybe later. Okay? Mm-hmm. Yeah, for sure. So that's something you want to think about, whether it's really appropriate to really impose that constraint back to the model, right? Mm-hmm. Okay? All right, guys, any more questions? Okay. Very good. So I think we finished a very thorough discussion about a single model. So that really tells you the essence for this course. We learned about math, and now we try to apply that math to here. Even for simple model like this, it's not that trivial to really prove something. But we'll see even more models coming. Okay. Right. So why don't we say I got about 13 minutes or so. Let me at least go over the programming test number 1 guide with you to see if you got any question. If you want to ask, if I can think about any tips, I can talk about it. And then you'll receive the practice question very soon. I'm still finalizing it with the TA. And by the way, for today, if you want to ask a question to the TA, Andy will still be there during the lab session if you want to ask him. And then for your lab number 2 solution, I may not have time today, but as I said, I'll maybe record some short video just to walk you through some difficult concept and something you want to watch out for. Okay, that's what I will do. All right, so let's now take a look at your programming test 1 guide. In case you haven't read it yet, let's read it together. If you go to, again, the lecture site, you will see programming test number 1 guide over here. Okay, let's take a look. Okay. Okay, so it's going to be next Thursday. And it will be from 11:30 to 12:30. All the machines will be rebooted about 11:25-ish. So try to arrive earlier. I might just be able to allow you to enter the room earlier. In that case, once you see the machine has been rebooted, you can just get started. So that can give you more time. But maybe we're talking about maybe 1 or 2 minutes, not too much. Okay. But anyway, just make sure you arrive in time. It's going to be the same place, Williams Small Center, 106, 108. There will just be certain seats on 106 that will be reserved, but I'll let you know, so you don't need to worry too much. Right, strictly individual in person, that's obvious, 10%. Okay, so this is really important. So this is not multiple choice anymore. It's purely a programming test. We want to know how well you can construct context and the machine in valid syntax, which means we don't want to see any errors in your machine, in your submitted project. Okay. So you'll be given 1 hour, and you're going to use the rodent tool only. And feel free to bring any sketch paper. It's 100% OK. Do you need calculator? I don't think so. Bring it anyway if you want to, if that can help. And during the test, you don't have any reference about the syntax except 1 document, which I'll refer you to. That's actually the document I already linked to you since lab 1. So that one should be something you have gone over already. If you haven't, now will be the time to do it. So in the test, you will have to use the rodent tool, and you will do everything from scratch. Nothing will be given to you. right? You will have to follow some PDF instruction, which will tell you, okay, now create this project, create this context, create this machine. And then there will be some description about, let's say this is a problem we want to solve, and then we want you to create maybe this constant, and formulate this particular description as axiom number 1, formulate this constraint as invariant number 2, and etc. So you will see some idea when you see the practice question, all right? Okay, so you got to do everything by yourself, and then at the end, you will have to, there's something here that's also very important. So I think that there will be several TAs who are going to grade your work for the programming test. But to really make our grading process smooth, we're going to suggest some exact names that you have to follow. For example, we might say, now, declare one variable called X or C. In that case, you have to make sure you keep that variable name exact. Don't use any other variable. Otherwise, when we look at your invariance, we wouldn't know what this variable might mean if that's not really mentioned in the instruction, right? Just make sure you follow the instruction faithfully. And you don't really, you are not expected to do anything to do with the prover, not really. Okay, so if your model is 100% correct, following all the instruction given to you, and you got all the proof obligation discharged automatically, you're good. Okay, and I would say the bottom line, you don't want to have any syntax error or type error. Having some proof obligation undischarged, you will still get partial marks. Okay. And of course, I'm going to keep reminding you during the test to really say you want to know how to export the Rodent project as a zip file. I think that's what you did, right, for your lab. So you will have to make sure you do that maybe every 15 to 20 minutes or so, and then you want to submit periodically to back up your work. All right, so submission for grading, you will submit as zip file, the project archive for grading. And then you want to make sure you don't really submit the wrong thing. But since we don't give you any starter project, so very unlikely you will submit the wrong project. Anyway, you want to double check. Okay, so this grading criteria here is only general. There might be certain specific details that we might add when we grade your project, but that's a general principle. Okay? Okay, so number 1, you want to make sure that you have no syntax or type error. Otherwise, TA will try to maybe fix the stuff for you. At least we can see if all the proof obligation can be discharged. We might maybe look at your invariant, even though it got error. We'll try to look at that maybe to see if we can give you some partial mark. But whatever we got, you're going to have some penalty because you want to really make sure you write the syntax right. Like a Java programming test, right? You want to make sure you submit something that can compile. And this one here is also to make sure you follow exactly the names of the variable or anything like a constant, variable, events, event parameter, axiom, invariant. Make sure all the names we suggest in the instruction are typed verbatim. Okay. Okay, so I think most likely we will expect after you encoded everything, then there should be no undischarged proof obligation. Okay. If there are any, but that's okay. We might deduce some mark, but you'll definitely get what you have written. We'll judge. Okay. So what does that mean? That means sometimes even though you think what you have written is already correct, maybe you have to formulate maybe the stuff a little bit differently. I'll give you one hint. Back in lab number 1, I think when we talk about maybe transfer events, right? If you try to use maybe just union operator for the transfer, that one may not make the prover happy. On the other hand, if you try the overriding operator, it can make it work. So that's why in the solution, we use the overriding operator. So the lesson is, even though multiple things are logically equivalent, but the prover might treat it different way, treat it differently. So you may want to try different alternative. Okay, for the format, you will be given some documents on the desktop on in your lab test. So this will be given to you, right? So this one here should be quite familiar to all of you. This has been given to you since lab number 1. So you can look at that to see the syntax for different operator or function or relation, etc. Right? You can assume that you will only need what we cover in the review lecture about the math construct in the actual programming test. Anything that we didn't really cover, I don't think you will need it. Okay? But we cover quite much, right? Okay, let's go a little bit further. And what should you review? You definitely want to review lab number 2, right? Which I'll try to go over in a short video with you. And it may not hurt to review the math construct, especially relations, function, different relational operations just to brush up. And also how to find the syntax in this document here. And for lab number 1, especially you want to review, the bank operation, you got a PDF solution already. Go over them quickly. And also make sure you know how to create a machine, create a context, create a variable, etc., and how to export the zip, right? Yeah, I'll make the practice question available to you fairly soon. Hopefully by the end of tomorrow, so you can try. And then over the weekend, I'll let you struggle a little bit with the practice test. And then next week, I will make the solution, at least make the solution available to you. But if we can make some time, maybe I can drop by one of the lab sessions and go over the solution with you. Yeah, we'll see. Anyway. And you can also look at this part over here to see how you can simulate the programming test, using the remote lab. The look and feel for the rodent will be just the same in the actual lab test. So just try to use a remote lab to practice. All right, guys, do you have any question about a programming test? I have 4 minutes. Go ahead. Yes, I'll definitely give you like an E or R description with just bullet points, like lab 2. Yes, I would say it may not be so obvious. Like say, I would say, write an invariant as follows for all elements in this particular set, and that wouldn't be that obvious, but it should be like a good hint for you to know what to write. You'll be given instruction for sure. Adnan. Yeah.
When you save it, it doesn't have any compilation error, but when you come back to it, what visible? Some event doesn't work, you have to save it.
I'm not exactly sure what happened, but I would say if let's say you save everything, and then on the rodent, if you right-click on the list of proof obligation, you can say retry all the proof obligation. Maybe before you submit, make sure you retry, and everything actually proved, and then save, and then submit. If that really happened, we can talk, and then we'll see what happened. Yeah.
Also one thing, it says that we have to launch rodent
Yeah.
under activities.
Uh-huh.
Is that how we do it, or we do it from terminal?
Terminal. I think if you go from terminal, make sure you launch the right version. I think 3.7 is the version. So yeah. So here I'm just giving maybe the most straightforward example. But as long as you can launch the right version of rodent, you're fine. Yeah. Guys, any other question? All right. Yes, Ryan.
Is there a reason why doing equivalent expressions in rodent?
Yeah, it's a very good question. So remember, let me address this, and then we are done. So the reason that sometimes you write some logical expression or several logical expressions, you think that's really equivalent to a single one that's in the solution. Why would prover treat one thing and differently than the others? After all, the prover is still just a program. Somebody wrote it. And when they wrote the prover, they kind of favor certain pattern of the specification, so they can make a decidable problem for them to solve. So I think, that's kind of the general hints. So that's why it's a very common practice. If you try to specify your model in a way that wouldn't work, maybe try to specify in a slightly different way, it might just work. It's just the limitation for the prover. No way around. Yeah. Yes? You will lose some marks, but it wouldn't be major. Definitely wouldn't be. So I would say, so that's why I really want you to also try. Let's say during the, very good question. Let's say during the test, you follow the instruction, you try to specify something, and then somehow proof obligation does not really get discharged. If you firmly believe what you wrote is actually right, try to see if you can maybe specify that in a slightly different way. That might just make the proof a proof. Or maybe it could be that what you believe is correct is actually incorrect. So when you come to me for feedback, I might tell you, oh, what you think correct was actually incorrect, and then we can talk about it. Yeah. Good. Yes, one more, and then I should let you go. Yep, so I would say that's something we'll make it clear. I think as you cannot really introduce new variables or new constant, but you want to add some extra guard, that should be fine. Guys, thank you so much. I'll reach out to you very soon.